So today we're going to be talking about logarithmic and exponential applications. So just like with any of our other types of equations, there are real-world applications that go with logarithms and exponentials. Now we've talked about a few of them when we did our graphing project, but now we're actually going to get into the equation side of it, where we're actually going to try and solve the equations for different types of models. Now, the first thing that we need to look at are the different types of models that we have. Now, all it means by a model is basically that it's an equation that can model or kind of be used for a specific type of application. So our first one is an exponential growth model. And so we have y equals a times e to the bx. So a and b are just going to be constants, and they're either going to be given to us or we'll be given enough information that we can find them. Now our exponential decay model still has a base of e, but now your exponent is going to be negative, which is going to, remember, horizontally reflect our graph, which means that it'll be decaying or decreasing instead of growing. The next one is called our Gaussian model. We see this more once you get into upper level mathematics like calculus and things like that, so we won't be doing much with that in here. And then our last two are used quite a bit. These are our logistic growth model and then our logarithmic models. So some of my text got cut off, but I'll read it to you. It says the amount S in billions of dollars spent in the United States on mobile online advertising in the years 2010 through 2014 are shown in the table. A scatter plot is shown below. So basically, this is the amount of money spent in the U.S. on online mobile advertising. So it says, an exponential growth model that approximates the data is S equals 0.00036 e to the 0.7563 times t, where t is in between 10 and 14, where t represents the year, with t equals 10 corresponding to 2010. Compare the values found using the model with the amounts shown in the table. And then again, it cut off some of my text. So according to this model, in what year will the amount spent be approximately $65 billion. Okay, so our first thing it asks us is to compare the values found using the model with the amounts on the table. So the way that we can kind of do that is by plugging in some values into our model. So let's go ahead and make another row of our table and say that these are going to be our model values. So you would want to use a scientific or graphing calculator to plug those numbers into, because otherwise it's not going to be very pretty numbers, so you wouldn't want to do it by hand. So you would use your S equals 0.00036 E times 0.7563 times T. And then we're going to plug in each of the values between 10 and 14. Be careful because we're not plugging in 2010, we're just plugging in 10. So if you were to plug in 10 into our model, we should get approximately 0.69. If we plug in 11, we're going to get 1.47. If we plug in 12, we're going to get 3.15. If we plug in 13, we're going to get 6.70. And if we plug in 14, we're going to get 14.28. So notice that overall, our values are pretty close to each other. But notice that the farther that we go along, the more discrepancy there is between the actual number and the number that we get from our model. And the reason for this is because remember that it is an exponential function, and so the farther out we go using that same model, the more potential there is to get an error. So that's why when we're looking at models, most of the time it's going to say that this models the situation from a specific year to a specific year. It's not going to say that it models it forever. But we can see that they're relatively close. So then it asks us to, according to the model, in what year will the amount spent be approximately $65 billion? So in order to figure this out, okay, this time instead of plugging in for T, we want to plug in for S. Another place to be careful about is, notice that it says that we are in billions of dollars. So this is the amount spent in billions. So when we plug in for S, we don't want to plug in 65 billion. We just want to plug in 65. So we would plug in 65, and it's still going to equal our lovely decimal. And now we want to solve for T. So this time we're looking for the time that we got 65 billion. So our first step would be to divide by that 0.00036. And I'm going to go ahead and leave everything exact until the very end when I'm going to plug it all in to my calculator at the same time. This helps us reduce the amount of rounding error that we have, because if we round as we go, it's going to basically make that rounding error bigger and bigger and bigger. So then notice that we have an e to the power. So just like our other exponential equations, we want to try and either 1, write it with the same base so we can use our 1-to-1 property, or 2, take a log of both sides. So since we have an e, there's not going to be a way for us to rewrite it with a base of e. So we want to go ahead and take the natural log of both sides. And remember that when we take the natural log of e to some power, the whole reason why we do that is because our natural log and our e are inverses, so that means that it's going to reduce one another. So we're just going to be left with whatever is in the exponent. So on the right hand side, we're just going to have 0.756t. So then our last step, notice, is going to be to divide by that decimal that's in front of t. So we're going to get t equals the natural log of 65 divided by 0.00036. And that's all going to be divided by 0.756. Now be careful, because that 65 divided by our decimal is all inside of our logarithm, while the big division by the 0.756 is outside of our logarithm. So when we plug that in, we're going to need to make sure that we end our parentheses after the 6 when we're plugging into our calculator. Now if we plug it in to our calculator, we're going to get approximately 16.004. Now, if we recall, remember that that doesn't equal the year 16. That's going to equal 16 years after 2010. So this is going to be 2016. And so that would be our final answer. And if we were to go ahead and double check and see how much was actually spent in the year 2016, it was about they said 45.95 billion. So a little bit off, but still kind of within the realm of reason. Alright, so let's look at another example. We've kind of talked about in several of our graphing examples how this can be used for population. It can be population of people, population of animals, and in this case we're specifically going to be talking about population of flies. So it says, in a research experiment, a population of fruit flies is increasing according to the law of exponential growth, and that's going to be important. After 2 days, there are 100 flies, and after 4 days, there are 300 flies. How many flies will there be after 5 days? And the reason that the law of exponential growth is important is because that tells us that we're allowed to use our y equals a times e to the bx power equation. And we know that that's going to simulate the population growth pretty accurately. Now, we know what our x is going to be. Our x is our time, and so we know eventually we're going to want to plug in 5 days into our x. However, we should notice that right now we also have an a and a b value, and we don't have any numbers to plug in for that. And so in order for us to be able to figure out how many flies there are after 5 days, we need to know what a and b are. And before, remember I told you that either they're going to give you your constants or they're going to give you enough information to find your constants. So in this case, they give us 2 instances. So 2 days there are 100 flies, and 4 days there are 300 flies. So we're going to use those 2 cases and plug in those values for x and y. And then we will have 2 equations with 2 variables, a and b. And so we'll have a system of equations that we're then able to solve for a and b. So let's go ahead and plug those information in. So we know that after 2 days, there were 100 flies. So 100 is going to be my y value. And 2 is going to be our x value. Likewise, we know after 4 days, there were 300 flies. So notice we have 2 equations and we have 2 variables. We need to either solve for a variable, or we could try and subtract using our elimination method. Because we're multiplying by that e and our b is in the exponent, the elimination method is going to be a little difficult. So what we're going to do instead is the substitution method. So we're going to go ahead and try and solve. So notice, I'm just going to simplify a little bit. So we have a times 2b. So if we wanted to go ahead and solve, let's say for a, we could just divide both sides by e to the 2b. So now notice, if I go ahead and plug into my second equation, now I know what a is. I can plug that in for my a that I have in my second equation. So I'm going to get 300 equals 100 divided by e to the 2b times e to the 4b. And then we just want to try and simplify as much as possible, and we're going to try and solve for b, because notice that that's the only variable that's left. So first off, notice that we have 2 things that have the same base that both have exponents. So in order to be able to simplify that, anytime that we're simplifying things with the same exponent, we're going to use our exponent properties. So if we were to simplify this, notice we could rewrite this as 100 times e to the 4b divided by e to the 2b, because my e to the 2b would be in my denominator if I multiplied straight across. Now this allows us to be able to subtract our exponents, so we would have 4b minus 2b gives us 2b. And now, since we only have one item that's being raised to an exponent, we can go ahead and try and solve for that, get it by itself, and then we can take a natural log. So notice my first step is going to be to divide by 100. So we're going to get 3 equals e to the 2b. Then we're going to go ahead and take the natural log of both sides. And remember that when we take the natural log of e to any power, it's just going to be that power. So then my final step is going to be to divide by 2. And that divided by 2 is on the outside of my natural log. Now what we want to do is plug that back in so we can solve for a. So we know that a is equal to 100 divided by e to the 2b. Well, now we know what b is. We know that it's the natural log of 3 divided by 2. So notice that my 2's are going to reduce. So we end up with 100 divided by e to the natural log of 3. And again, remember that e and the natural log are inverses of one another, so they're going to reduce each other. So we're just going to be left with 3. So we get that a equals 100 divided by 3. So now, after all of that, remember that our a and our b are not what we're actually looking for. We want to find our overall equation. So now that we have those two things, we can use those to plug in to our original equation. So we have 100 divided by 3 times e to the natural log of 3 divided by 2 times x. So if I asked you to find an equation that represents this specific instance, that would be your answer. Now, for us, it's asking us how many flies do we have after 5 days. So what we're going to do is use that equation that we found and plug in 5. And again, because you have some not super nice fractions and you have e's, you would just plug all of that into a calculator, and we get that we are approximately 519.615. Now remember that we're talking about a real-world application in this problem, and so we're talking about flies. We don't really want a decimal of flies, so we're going to go ahead and round up. So we have approximately 520 flies after 5 days. And so that would be our final answer. Now, this was a problem a little bit on the longer side. That doesn't mean that it's super complicated, but there are quite a few steps. And we do have to be fairly comfortable with solving equations and also manipulating your natural logs and your exponentials. So if we're still having issues with our exponential or logarithmic rules and properties, make sure that we go back and kind of review those first before we start trying to solve some of these equations. So in our next example, we're actually going to be looking at a very large place that we can see our exponentials come up, and that's in carbon dating. So carbon dating is where any living or used to be living thing has a certain amount of carbon in it. And depending on how much carbon is in it or how much carbon is left, we can use that to estimate how old it is. And this is used quite frequently when trying to date fossils. So it says to estimate the age of a newly discovered fossil in which the ratio of carbon-14 to carbon-12 is R equals 1 divided by 10 to the 13th. So R is that ratio, that's what it stands for, and our model that we're going to be looking at is R equals 1 divided by 10 to the 12th times e to the negative t divided by 8,223. So notice here we have an exponential decay model because over time, the amount of carbon in an object is going to be decreasing. So what we can do is kind of like we did on the last example, we're going to work our way backwards. So we're going to say, I know what R is, or what the ratio is, so we can plug that in. So I'm going to say 1 divided by 10 to the 13th power is going to equal the model that they gave us. And then we just want to solve for t. Now remember, before we start taking any logarithms or doing anything else, my base needs to be by itself, which right now it's not. I have a 1 divided by 10 to the 12th. So in order to get rid of that, we would need to multiply both sides by 10 to the 12th. Well, notice that if we do that, 12 of my 10s are going to reduce, so I would just be left with 1 10 in the denominator. And then our e is by itself, so now we can take the natural log of both sides. When I take the natural log of both sides, remember that my e is going to reduce with my natural log, so we're just going to be left with whatever was in our exponent. So then our last step is going to be to multiply both sides by a negative 8,223, which will give me my t. If I asked for the exact answer, that would be our answer. However, when we're talking about years, we want to go ahead and plug that into our calculator and approximate. And we're going to go ahead and round to the nearest whole year. So we would say that this is 18,934 years old. And that would be our final answer. All right, in our next example, we're looking at the spread of a virus. And if we go back to our original model, this is going to be our logistics model. And the reason why logistics models are important is because they model exponential growth with a limiting factor. So these graphs are going to look slightly different. So our normal exponential graph, remember, looks like just keeps going up and up and up and up forever and ever and ever and ever. It looks like that. Now our logistics it starts off looking very similar to a exponential, but then eventually it's going to slightly taper off and get closer and closer to some value. So our logistics model actually has two horizontal asymptotes, one on bottom and one on top. And we see these happen a lot in things that are limited by specific factors. So, like if we're talking about population of animals, population of bears. So your population is going to be dependent upon the amount of natural resources, the number of predators in the area, anything like that. Same thing with like sales or things like that. Usually after a while, it's going to taper off. So a logistic model is actually much more representative of most of the applications that we're going to be looking at in the real world than an exponential growth. The same thing with like the spread of the virus. So you have a specific amount of population, and usually you're going to get really close to that full amount of population, but you're never going to hit everybody catching a virus. And even if you did hit everybody having it, eventually people are going to start to not be getting it anymore, or it's going to go away. And so that's why it tapers off, and it's not going to continue to grow forever. So in this case, we're talking about the spread of the flu. So it says on a college campus of 5,000 students, one student returns from a vacation with a contagious, long-lasting flu virus. The spread of the virus is modeled by y equals 5,000 divided by 1 plus 4,999 e to the negative 0.8 t, where t has to be positive, where y is the number of students infected after t days. The college will cancel classes when 40% or more of the students are infected. So part A, asks us to find how many have been infected after 5 days. Well, since we know that T is time and Y is population, we know that we're looking for Y. So we're going to plug in 5 for T. And we just want to use our calculator at this point. So we would get that Y is approximately 54.019. Again, because we're talking about people, we want to round to the nearest whole person. So we would have 54 students. So then part B asks us, after how many days will the college cancel classes? So notice that it says the college will cancel classes when 40% or more of the students are infected. So we know that we're going to be plugging in something for Y this time and solving for T. But be careful, because we're not going to plug in 40. We want to plug in 40% of our total population, which is 5,000. So 40% of 5,000 is going to be 2,000. E to the negative 0.8 t. And now we want to solve for this. Again, we need to get our E by itself first, but be careful, because right now our E is on our denominator, which we don't want. So we would want to actually multiply both sides by that right side denominator, because that's going to allow us to get the E into our numerator. So then we would want to divide both sides by 2,000. And notice that if we take 5,000 divided by 2,000, we're just going to get 5 halves. Then we want to subtract 1 from both sides. Again, I'm just trying to get that e by itself in order to be able to solve for t. Eventually, we're going to have to take the natural log, but we can't do that until the e is by itself. So if I subtract 1, I would be 5 halves minus 2 halves is 3 halves. So then we would want to divide both sides by 4,999. But remember that dividing by something is the same thing as multiplying by the reciprocal. So we would be multiplying by 1 divided by 4,999. And then 2 times 4,999 is going to be 9,998. Well, now my e value is by itself, so we can take the natural log of both sides. When we take the natural log of both sides, remember that it's going to reduce with my e. So we're just going to be left with our exponent. And then we have the natural log of the right-hand side. Then our last step is going to be to divide by that negative 0.8. Again, remembering that the negative 0.8 is outside of my logarithm because I've already taken the natural log. So then our last step would be to plug all of that into our calculator. Again, remembering that parentheses around my first fraction. And we get approximately 10.139. Again, we'll round. So we're going to say that this is going to be approximately 10 days. Alright, in our last example, we have a logarithmic example, and it's using the Richter scale, which is what measures the magnitude of earthquakes, which has become more prevalent in Oklahoma, so we've gotten a little bit more familiar with it. So it says on the Richter scale, the magnitude R of an earthquake of intensity I is given by R equals log of I divided by I naught, or I sub 0, where I sub 0 is equal to 1 is the minimum intensity used for comparison. So I'm not really sure why they go ahead and say that this is I divided by I naught when they tell us what it is. So we're going to go ahead and just simplify that. So we would get I divided by 1. So we're just going to get log of I. So that's really the model that we're looking at. So it asks us to find the intensity of each earthquake. Now remember, intensity is represented by R. Remember that intensity is represented by I. They give us the R Richter scale rating. So R in our first example is 4.0. So we would have 4 equals log of I. Now remember that if I don't have a base on my logarithm, it's an understood base of 10. So if we wanted to simplify this, we would need to raise both sides as a power of 10. Because then if we do that, my 10 base and my log are going to reduce each other. And so I just end up with I. So plugging that in to our calculator, we would get that I equals 10,000. So part B is going to be very similar, just this time we're plugging in 7.8. Again, raising both sides as a power of 10. So we get that I equals 10 to the 7.8. We would need to plug that into our calculator. And it is going to be kind of a big number. So we get that I is approximately 63,995,734.45. And that's going to be intensities. So basically it's using, again, that 1 as a baseline intensity, and then it's saying everything else is, you're saying how much more intense that earthquake is than a baseline intensity. And the way that they measure that is, if you've ever seen kind of like those in a movie where it shows like the little device going up and down and making the little like wavelengths, it's actually measuring how many wavelengths or like kind of like vibrations there are within a certain amount of time, and then that's how it measures the intensity of a given earthquake. So those are just a couple of examples using exponentials and logarithmic equations. There are many more, but that gives you a basic idea of how to use and how to manipulate the different types of equations that you could see.